Please.
Hello, everyone, and welcome to our first session of the Young Scholars Symposium. Today we have 3 speakers, and I will be the moderator. Today's session, my name is Virginia Melnick, and our first speaker will be Dan Luo and from Queensland University, and our second speaker will be Nick Bao from RMIT University, and our last speaker will be Hua Chai from Tongji University, and they'll be presenting in that order. And after each presentation, we will take some answers and questions and brief discussion on their research for this session. So this is the first session of 4 sessions, and the topic for this session is Advanced Fabrication and Robotics. The next session will be at 8 p.m. China time and will be on AI and human-machine interaction. The third session will be the next day at 9 a.m. China time on hybrid forms and virtual architecture. And our final Young Scholar Symposium session will be that evening on Sunday on innovative structures and materials. This, of course, is part of our larger doctoral consortium, which you can find out more information on the website, which is an ongoing session of lectures and courses for doctoral students and in architecture and design. And here is our first session speakers, and I am the moderator. And I just want to remind everyone also that the Architectural Intelligence Journal inaugural issue is launching soon, and Philip Yon will be the editor-in-chief, and it is currently having an open call for papers. So please check out the website here for more information on how to submit your papers to the journal for peer review, because this is a wonderful opportunity. Thank you. So I will begin by just passing it over to our first speaker, Dan Luo.
Hi, thank you very much, Virginia, for your introduction. I'll just quickly start sharing my screen. Second. So hi, good morning, everyone. My name is Dan Luo. I'm a current lecturer in University of Queensland in Brisbane, Australia. So in this session, I'm just going to share some of our recent research and explorations in applying for FRP for large-scale automated constructions. They're not at the endpoint or finalization of huge projects, but it's just showing the progress work that we have accumulated so far and the sub-process of getting there. Hopefully it can inspire for the be an inspiration for the students and the PhDs who are struggling along their ways. So the reason that we're working on FRP is that compared with traditional construction materials, FRP has a few significant benefits. For example, they have a high strength, high stiffness, their corrosion resistance, it has high durability factors. They're actually quite commonly applied in aerospace and on structural reinforcement. And it is at the price point of like mass manufacturers that are at a price point that are feasible to be applied in construction industry in a large scale. However, this material has never been considered as a traditional construction material such as concrete, bricks, timberworks, and etc. So, and also in University of Queensland, we have a very strong aerospace research as well as FRP research labs. So a lot of the projects were developed in collaboration with them. Of course, recently there are a lot of influential researchers that are trying to apply such materials in architecture and construction. So some of the most influential body of work are from Archimedes groups in Stuttgart that look at different ways of using those kind of coreless winding method to construct this kind of large spatial geometries or components that is distinctly different from how we normally consider construction components to be. They are mostly utilize robotic winding method, which is just inconsistent with how are we usually fabricating those kind of FRP components in industry, either for aerospace or for automotive, mobile, and etc. Most of them requires prefab formwork, so and the anchor points for them to be mounted on. And those kind of formwork can further be used as like connection joints that extend the structure, connect one component with another. So for our research project interest and exploration based on the research strength in the University of Queensland is that we're trying to think about to develop on the existing body of research and explore if we can fabricate them in a more systematic but more, let's say, sustainable method way, which reduce the use of those kind of single-use formwork and while be able to accommodate wide diversion of geometries. Also, we're looking at how those kind of FRP can be used to fabricate components that can be synthesized or can be combined with existing industry workflows. So the first project that we're going to introduce is just is developed in collaboration with Nick Bob. So you will hear his presentation following mine, and it is recently exhibited in Melbourne Design Week. So I'm just going to quickly go through them because I'm aware I only have 20 minutes. But the interesting from this project is that this project actually started with a very smaller starting point, means that we want to develop a project for an industry training workshop. So that's which is for structural engineering, so they can see the potential in innovative structure system, in mass customization, novel materials, and the robotic fabrication. So we developed this kind of the truss system for a table and use the finite element models to analyze the strength distribution for each truss members, did a bit of structure testing, and optimized the distribution of strength on each of the truss members, which are reflected on how many strings of RP that we want one, which is translating to the cross section of the component. The fun thing about this part is that we combine robotic assembly with FRP winding. So the whole setup is that you have a base formwork of a structure setup, and first of all, we use robot, this simple pick and place mechanic, to place each anchor point at the correct location. In this case, you don't need to do all the prefab formwork, but rather we have an adapt system that can place the anchor point for each variations. So once the anchor point is placed and jointed, that we are able to wind the trusses with reusable anchor system. So this is the iterations through our reusable anchor system that we settled with a combined hook, where the hook can easily be removed after the component is cured. And this is the outcome of our first prototype that are just mainly developed for a 2-day industry training workshop. And on top of that, we did notice a few very significant strengths of that system, which means that there is no additional need for fixed formwork. It is a very smooth workflow from identifying anchors to the winding, automatic winding. So we're trying to iterate that system into the next level complexity for our Melbourne showcase. So Nick did this part of the structure optimization system with Amoeba that I'm not going to go into because he's going to present it later. And then the structure optimization is both developed as a form finding method and to generate the distribution of pattern on the seashell. So each unit, as you see on the right, it contains two layers, CFRP layer, so glass fiber, reinforced fiber, which is more for generating the form, and the carbon fiber is for the structural reinforcement at core locations. And in this case, we have developed this kind of adaptive anchor system that basically are two parts that can be extended at different lengths. So, and they can be anchored at different orientation in relation to each other to accommodate different geometries, the base anchor point for each unit, and we use robotic pick and place them at the right spatial orientation. We develop an anchor point that are made of those kind of ball head hinge that I can accommodate different angles of, let's say, placements. So this is the formwork that we're using, and here are some completed components because we develop it in quite a condensed schedule. We did not have too much documentation during the process, but this is what the final result looks like when we fully assembled them at the Melbourne Design Week. So this is like a very quick exploratory project that came from small initiative of satisfying our curiosity of how to develop this kind of reusable and adaptive anchor system. Yeah, so this is just some of the process. For this so this is our final assembled outcome. The second one I'm going to talk about is a parallel project that we're working on. So, I mean, like the fiber winding is fun and it's able to generate a lot of interesting geometric patterns that are responding to the tailored optimized outcome. with this kind of like topological optimization, etc. But however, one significant shortcoming for that system is that it's almost like those kind of 3D printed structures that itself is a standalone system that does not correlate to a lot of industry workflows in construction. So this is another project that we're working on to look at how to actually utilize those kind of carbon fiber to develop an additive process that can actually fit into the workflow of our construction practice. So this one is integrated workflow that combines robotic fabrication and the fiber reinforcement polymer again. However, the difference between this project and the previous project is that instead of using fibers itself, we're actually using FRP sheets and those kind of rollers. And instead of the traditional ways of those kind of layer by layer additive manufacturing, we're actually using the lamination process between the fabrics to increase our build volumes. So a significant benefit to this is that this is an existing building brick prototype that are developed in UQ. So the idea is that we're able to use those kind of fabricated FRP tubes to construct the, let's say, this kind of large-scale bridge structures in remote areas. The benefit of using these tubes are that they are very lightweight. They are industrially fabricated. It's something that you can connect with manual labors instead of requiring on some advanced mechanicals that are difficult to transport and expensive to use. So the way to connect them is basically for workers to wrap up the joints. So this is, and also the tube itself serves as a reinforcement to the casted member. So after joining the FRP tubes, they're going to cast the gap in between with concrete. So this is something that industry are already using. So our question is, instead of using those kind of mass customized uniform tubes, are we able to use advanced manufacturing robotic assembly to actually customize those tubes to different variants to accommodate certain geometric flexibilities and to generate more, to construct more efficient structure system, or just suits the need for our design intentions if we're designing those kind of non-uniform members or structure systems. So this is the system of concrete filled FRP tubes that are commonly used in industry. So the whole system, so this is only our first iteration. So we're working on our second iteration. So the first iteration is quite simple. We're just using a passive rollers where on one side it carries a row of FRP fibers, and on the other side it's just two compressive rollers that push the newly added layers to the existing layers. And the trick is to, so this is basically the process. So the trick is to make sure that the layers are able to self-sustain itself and avoid delamination. That is done by calibrating the epoxy resins, the cure time, so the ingredients that we use. So this is some of the earlier prototypes, and this is how the detail works. So you can see that the layers, how the layers extend, and where is the how the resin is infiltrating each layer. And the core is another element is that we have to maintain a dry layer in the inner surface so the roller can move without pulling the existing geometry, deforming the existing geometry. Yeah, just going to show. So basically, so the benefit of this, of course, compared to the original industrial workflow, is that first of all, it does not have the need for formwork, because those kind of standard fiber that you saw mostly relies on this kind of prefabricated formwork, and also it relies on the due to the limitation of the formwork, there are limitations in the geometries. While using this kind of coreless method, we're able to fabricate components with more flexible geometries. And of course, the ones shown here are our earlier iterations where it still has some problems, as you can see in the inner surface. The inner side is deformed from the roller applying the resin and the friction between the roller and the surface. That's something we're trying to resolve currently. So here are some potential outlooks of the application. So the forefighting is again done by Nick. Hypothetically, this one can be used to fabricate this kind of very gaudy looking typologically optimized structures without the need for customized formwork, and also share the benefits of adding additional strengths to the structure members and the ability to be easily assembled by workers manually. Yep. And here are some additional ideas that we're working on. So originally we're working on extrusion like linearly vertical to the ground, which has a restriction in the height due to the movement of robots. Now we're working on the more horizontal extrusions where we can easily extend the member length, which of course this is only for showcasing. It may need additional support in the middle. And we are currently working on a few structure tests to compare those kind of laminated tubes with the kind of industrial produced reinforcement, because this kind of lamination, the lamination is not as tight as the one you would expect from the industrial traditional way of fabrication, basically meaning rolling and tightening on a formwork. Yeah. So here are our sharing of our current exploration about additive manufacturing robotic assembly with based on, let me just stop here, with FRP. So thank you very much.
Thank you. That was really great presentation. And I have many questions and thoughts, but maybe since some of the projects were in collaboration with Nick Bao, perhaps we should just move forward to our next presentation and have Nick present, and this will probably bring up some dialogue between the projects. Thank you so much.
Thank you.
Yeah, can you see my screen?
Yes.
Is it presentation screen, right?
Yes.
Okay. So, hi everyone. Good morning. I'm Nick Bao. I'm from MIT University. So today, it's very honored to attend the Young Scholar conference for the first session at Advanced Fabrication and Robotics. So my main topic is about typology optimization for the robotics additive manufacturing. So I'm currently lecturer at the School of MIT School of Architecture and Urban Design, also working as a researcher at the CRSM, led by Professor Mike Shea. So in the past few years, I did quite a lot of projects. The main idea is about to structural performance driving generative design, robotics, 3D printing, fabrication. So back to the main topic, all the design and inspiration from the nature structures. And we are trying to look for the balance between the aesthetics and the performance. And to try to make the form finding more nationally. You make the how to use a computer to generate the national forms. So still back to the early stage, 1990s, Professor Mike Shea proposed this simulation of an apple shape optimization. Later on, he developed the BSO method for which is the main important topology optimization method in the world. So the structure design by myself and Dr. Xinye and Yulin Xiong on the screen, we won the first prize using the BSO topology optimization method. So you can see the material is being removed step by step, and also still keep the similar structural performance. So for more convenient for the designer can use the BSO method. So Professor Mike Shea's team developed this software which called Amoeba to can let more designers on the Rhino platform can use the BSO method more easily. So this is a digital design method. And now more and more the people using the topology optimization methods plus with the adaptive manufacturing, but mostly they use the small scale, the design and the fabricated small scale project, including the MIT smart nodes, Arab nodes, also this the jaw and the chairs. So we are looking for more architecture scale fabrication. So I'm working with the MIT Architecture Robotic Lab, led by Professor Roland Snooks. So we are using the KUKA robots to develop the larger scale 3D printing and construction techniques. So the main strategy for the adaptive manufacture is mainly about the clay, concrete, the polymer, and the wire metal print. Also related to my PhD study from the theory to method to application. So the most of the theory is related to the rules-based design approach from the swarm intelligence and the structure optimization. Later, developed the two different strategies for the optimization method. One is design algorithm for the skeleton design. Another one is for a real-time feedback, the algorithm for the larger scale agent body design. And most of the algorithm has been testing into the different architecture application. So start from the first project, Xform 1.0. So today I will talking about several projects to relate it to the same topic, but very briefly. So we try to biomimic from the tray system and also the column from the Gaudí's church to design the new column for the for our own pavilion, which is exhibiting Digital Future 2019 in Shanghai. So you can see the material is removing and also create the tree-like branches. Then this is a very experimental integrated topology optimization and robotic fabrication project at the beginning. So we tested using the small scale 3D printer to test the 3D model, and later on move on the robotic at MIT to print using the KUKA 150 to print the column. And after that, we clean all the stream and polish the surface and design the joint, detail joint, and move it to Shanghai Tongji University, and assemble with our students on site. So it's a very early project 3 years ago in Shanghai. Later, we developed another project which called XForm 2.0. This one is more advanced within the so this is the original form. Then we divide it into a quarter, into one piece. This is one quarter. Then we added the boundary conditions and also added the normal pressure load on the curved roof surface to using round the BSO method to remove and edit the material to create the tree branches pavilions. So on the left side is a quarter of the model, and on the right side is the full model. So after we're testing the structure of the pavilion, we just meet with actual structural requirements. Compare with the 1.0 and 2.0, you can find the difference. The 1.0 only have one flat surface, and 2.0 have 3 curved surface. Can create a more tree branches and more interesting. This is different between the seeding view of the XForm 1.0 and 2.0. And this is the side view comparison. So the similar progress, print the small scale 3D printing model and test if it can be printable. Because of we carried this model to Barcelona in 2019, so that's why we divided into the different pieces. It's about 25 pieces, and still using the same polymer robotic 3D printing techniques to print the different components and design the joints. And move to the we carry it with Dr. Xinye and Professor Mike Xie to Barcelona, and only you spend the 5 hours on-site assemble, and we never test it in Melbourne, and we directly build up it in Barcelona. So this is quite successful model, the project, and because of the limitation of the suitcase, so that's why we only build up 1/4 of the model. So this project called Cloud Effect, which is a several project. This one is another approach, which is using the small intelligent agent body systems to get the using the Kukuchia code to create the skeleton installations and pavilions for the fabrication and the robotic fabrication and additive manufacturing. So my main contribution is to develop the real-time structure feedback loop systems for the small intelligent methods. So you can see this is the skeleton and design for the one installation using the carbon fiber. So you can see the first iteration, there are the more red parts, which means with the much more high the strengths. So the real-time structure feedback loop can help it to identify which part has more strengths, then to adjust the algorithm to update to figure out which is the which part you need to add more fibers. So you can see the later, after several iterations, you can see there's the reddest part is reduced, and to keep the most efficient carbon fiber structures. So for the external layers, we're still using the robots to print the shell. So you can see this image about the several the layers. The external layer is a 3D printed layer for the shell system. So the internal, the black and the steel, the black system is the carbon fiber infused. So we also presented in Digital Future last 2020. So that's why we call this super composites, because it's using the different multiple materials to develop it. So this is the animation. You can see the different layers showing the intricate forms and the intricate intricate systems. Then we also fabricate and bring it to China to expand in the Shenzhen, Hong Kong, by city Binali. And after that, we developed another project last year and expand in the NGV pavilion, and we also improved the algorithm for more the better speed and also more accurate. Because this project is have two parts. One is on the wall and then one is on the underground. So this is the fabrication method. The design method is very similar, but the only difference is the last project in Shenzhen Biennale has we have divided more pieces. But for this project, we print the whole piece at one time. So it's so the carbon fiber has more continually structure. So we exhibit in NGV Pavilion and get a lot of visitors to there. So you can see the printing quality is much better than which is in Shenzhen, because we're also improving the printing quality and the printing path. So this project called cast bodies, also very similar process using the robotic to print the and the mold to print the envelope of the project using the aging bodies one intelligent with some optimized structure optimized algorithm to identify the whole the form finding of the project. So this project is different from the last project. We use the concrete to cast, use the high performance concrete to cast into this printed formwork, and to test if this formwork can work or not. So this is a final project which is have already casted the concrete, but this concrete is very hard to remove. So we call it is sacrificial formwork. But if we can remove the foam, remove this plastic foam, it can still works. But the only problem is we destroy the formwork using the heat gun. But this year, I work with another PhD students and Professor Maxi. We're working on another removable formwork using the plastic 3D printer. Maybe in August and in September, my colleague will present the similar project. And also last year, using the similar strategy to design the aging bodies, also collaborate with the China construction and technology to print the formwork, which can be removable and cast the high UHPC concrete. Then after demolding, we get this concrete geometries. Ideally, if we can print the 12 pieces of these components, it's possible to make the whole installations all move into the more intricate facade design or interior design. And in the past 2 years at MIT, we now more focusing on the metal, the wine printing, the metal 3D printing, and using my cast body as the example to test the geometries. This video is from 2020, as we're working with University of Wollongong and to print the first cast body metal print project. So this is the first type of this printing technology. Later on, from last year, Roland Stux and I and our colleagues to develop the systems, the metal printing systems at MIT, and Roland is the leader of this installation design, and we working together to make this project down. At the beginning of this year, attend the Melbourne Design Fair, Melbourne Design Week. So this is a final installation. The design process is very similar, but using the real-time structure feedback, also using the metal printing. But this project is more successful because of this is the first largest 3D printer of the Swan intelligent and the multi-agent algorithm-based project. And with the very high good qualities, the printing qualities. So this project is made of 12 pieces of the agent bodies. And the next project I want to introduce is the intelligent foam, which is presented last year in Digital Future, working with the China Construction and Technology, and we're using the BSO topology optimization method to do the foam finding, added the loading on the surface, and set up the boundary conditions and run the BSO methods. And later we remodeling the project and easy for the 3D printer, 3D printing. Then this is the first small scale 3D printed model in Melbourne. Then we tested in the Abacus for the structural performance. Then we divided for the large prototypes, we divide the model into the different pieces for the 3D printing the mold. So this is the mold design. We're working with the Dr. Cho Wei and Panjanan for the construction. So this is the middle part of the project. Then we send it to China for the fabrication. So this whole piece of the formwork is 3D print by 3D print, and this is the middle part. On the right side is the left part, the side part of the project. And later, we using the UHPC concrete to spray on the formwork. So this is the process the workers they are working on spray the concrete on the foam. So this is the first layer of the spray the UHPC concrete, and this is the last layer for the concrete spray. Then this picture showing the after demolding, then they polish the surface for us to try to remove the most of the seam line of the surface, and this is the middle part, and the middle part after demolding. Then the project has been sent to the Tongji University for assemble with our students from the Digital Future intelligent foam workshop. So each piece is about 150 kilograms, so it's very heavy. So the builders and the student working together on site to try to assemble it. So the sample process is quite fast. It's always reduced the assemble and the construction time on site. So it's a good, it has a good potential for the later prefabrication progress construction. So this is the photo sent from the students. So it's the last step for. So the video is taken by students showing the final outcome. Because of the workshop is very short, it's about just 7 days. So that's why we still keep, you can see the two lines, the wire lines behind the model, because the concrete have to cure 28 days for the best performance. So after 28 days, the wire support the steel wire support behind can be removed. So this is the some nice photo from Shanghai. And this project is intelligent force printing. As we invite Professor Philip Yuan as a visiting professor at MIT Architecture last year, and build up this concrete 3D printing project at IT Uni and Fabric Uni. So this is located in Shanghai. Just very quickly to talk about the design progress. So this design is integrated with the polyframe generative design algorithm developed by the machine from UPenn, and also integrate with the topology optimization method. So we ask students to do like a pavilion design competition. Then we choose the best results and for the further design development. So firstly, student design the using the polyframe design the overall form finding for the skeleton. Then later using the topology optimization to help with the material optimization and reduce some unnecessary materials. So you can see the setup for the topology optimization method working on this project. And later the project has been finalized and for the 3D printing and checking the force analysis. Also divided and put the steel bars for the reinforcements, because this is the largest project for 3D printed concrete, and also with the generative design methods. Then we divide this project into the different pieces for the 3D printing and print different components and testing using the small scale 3D printers and using the FU robots developed by Professor Philip Yuan. So it's very good platform for using the robots and print different components and also assemble outside in Philip Yuan's office. And so the builder working with the students on site for the assembly. So this is the final outcome. It's a quite large scale for and more intricate curved 3D concrete printed project. So the last project I want to introduce is the weaving tectonics, which is the project I'm working with Dr. Dan Luo from University of Queensland. I think most of the robotic fabrication part has been introduced by Dr. Dan Luo, so I'm just quickly introduce the design process. So this is the main design methods to integrate with BSO method with the Reno working platform. So I developed this design progress with Dr. Xin Yan. I think he will introduce the similar topic tomorrow night, and to develop this grasshopper systems for can help with the detailed control strategy for the topology optimization in architecture design and development. So we set up the form and also added the gravity, set up the form and boundary conditions. After 60 steps of iteration, get this the shell system pavilion. So this is the video. I think Dan already showed this. And later using the robots, self-designed robot systems by Danlo's team for the welding for the weaving carbon fiber systems. So after they fabricate the whole part of the components, then they carry it to Melbourne, and on site, well, we assemble the pavilion together for the Melbourne Design Week at the beginning of this year. So it takes just only 2 days for the fabrication and assembling progress. So it's a very fast construction method. So finally, this is the final outcome of the widespan architecture and widespan topology optimized robotic fabricated project. So this is all the project I want to introduce today very briefly. So thank you for listening. If you have any questions, you can also contact me by email. And thanks for all the collaborated friends and colleagues.
Thank you, Nick. What a really amazing presentation, as always. I think there's so much to work that you've done over the years, and it's always clear the progression of how the projects are getting more and more detailed. One question I do have, though, is that because the way that the VESO method is kind of subtractive, and then you're working with additive manufacturing processes, and a lot of times scale is a struggle where things have to be printed in smaller pieces and then reassembled on site. Like particularly when looking at the video of the assembly for that Melbourne installation, you have a few students holding it up until you can get the other legs on and stuff. So have you started to study or think about these kind of assembly processes? And that's the same kind of question for Dan as well, because you're also looking at the same kind of constraints with the manufacturing can only go so large, but then the pieces you want to make have to be assembled on site afterwards and still by hand right now, it seems.
So I think it's an interesting question because after all, because construction is very different from, let's say, industrial manufacture where you intended to fabricate everything in one piece, like bicycle frames and etc. But in construction industry, it's nearly impossible, or it will be very restrictive if we're able to fabricate the entire thing in one go. So breaking down the scales and the connection has always been like consistent issues. However, most of our, let's say, the optimization method are mainly working on the end result, which means completed objects. So considering that, so I personally find that it's crucial to have the fabrication process being delivered in the same logic as the optimization process. So for example, like in that earlier winding project that we're working with Nick, like basically most of the force travels along the members, along the patterns, so that in this case, like each members on the pattern is working at the same direction as the translation of the force. So, and also the joints is like, instead of just gluing two pieces together, the joints are actually at the place where the loads are transferred. So in this case, we do find this kind of fiber polymers to have a strength in this area. So it means like the flow of the force can be easily visualized both in the pattern and both in the analytical models, and the joint logic, the surface pattern can all work in the same narrative, so that when it joins together, the performance, of course, there are still weaknesses at the joints, but the overall performance is more or less in the same narrative as the initial form finding process. So, and it's the same thing with the second, the second project where we're working with the spatial structures. So that one is actually where, even though they treat the end project as a volume, but we're working with a confinement. So the confinement is like typical reinforcement method that increases strength. So we're working with one aspect of the structural performance. However, as like building is a very complicated system, I'm not sure if we should simplify it into one system and just instead of working on like multiple facets of it. For example, connections, reinforcements, the initial the load model of the forces, and etc. So that's the interesting thing about building this. Even though we want it to be a very pure system, but it was never pure. Yeah.
Exactly. Nick, do you have any thoughts on that?
Yeah, very good question, because most of our project is divided into the small pieces and assembled on site, which is for the topology optimization is different. The structure actually, we didn't calculate the segment of the pavilions. So this brings us like the first project in 2019 with Roland Snooks. So that's why our on-site project always not very stable. So that's why we developed a second project with the continuous structure pieces in the Melbourne. I think as a similar with the intelligent force printing with Philip Yuan's team, because of so that's why they added the steel bars inside, which is continually. It's not segments. Only the envelope of the project is the segment, which is fine because it's not the structure based. Yeah, so this is very good suggestion. Later we can also consider about this dividing progress with the structure optimization or the topology optimization.
It's a really special opportunity. It's delightful to see what's happening recently from Australia. And I remember in 2014, actually in Digital Futures, we have the special topic in structural performance-based robotic fabrication. In that year, we invited MIDI-PADI developer from Boston, actually to introduce this kind of performance-based optimization structure tools, actually to deploy into the robotic fabrication process. I think I can see right now a lot of development happen around the world, and that is the real motivation, probably why we should address the robotic fabrication research. And especially from Rodan's research, I can see some very interesting creativity process which can engage into the teaching and the research. So the most challenge, actually, you're talking about the confinement. For example, the second circle weaving, fiber weaving project. So the question goes to the definition of this kind of circle-based winding or weaving pattern, actually, which produced by the tools. So what's the thing, the confinement for this kind of toolbox in the future? And if we want to deploy this kind of technology or details into the scenarios of the cotton connection, column connection, or the join different prefabricated discrete components into a holistic structure components. What's the challenge you want to meet next step? At the same time, I think this is a creative process to introduce this kind of a new industry technology into the architecture discipline. But I think if we want to go further, probably we should base on a lot of detailed or the cross-discipline research. Could you introduce the background of your research team and how do you organize such kind of research in your university?
Thank you very much, Professor Yuan, for your comment and support. So I do agree, it's a quite interesting project. So the reason we started at this area is that, so in one of the earlier showcase, we have shown that bridge that are actually built in UQ. So that one was our earlier inspiration. So we did notice that there are a few very significant strengths of that system. One is, as you mentioned, is a connection. So because normally when we're trying to connect 3D printed parts, especially in large structures to achieve structure integrity, it was such a challenge, no matter if it's those kind of the steel prints or the concrete prints. But what we have noticed in those kind of connection of those kind of tubular sections, it is quite simple. So basically you put the tubes next to each other. Normally they have internal steel scaffolds that hold them in place. And basically the workers just manually wraps the FRP fibers around the joint areas and apply epoxy, which can all be done with a manual process. And once it's cured, so like the two cube would join into a continuous structure components. that has this kind of continuation of the strength without the weakness at the joints. So that is something that we noticed is a special feature of the FRP, is this kind of extendability and the simplicity in jointing the components. So actually, that's something we're going to do next. So once we have completed the structure test of the individual component, we will be trying to join them into larger spatial components. And the second each question topic is about confinement. So the advantage and the weakness of this kind of tubular joints. The advantage is, of course, because it's a tubular confinement, it serves as a structural reinforcement. However, the problem would emerge if we try to deviate from that circular cross section. So it's possible for us to widen non-tubular sections. That's actually what we're currently doing, like to explore the geometric freedom. But once we deviate from the tubular cross section, at least the structure people would immediately ask us, what is its purpose? Because obviously it's not serving as structural reinforcement, because it's the distribution of force, it's not uniform, and etc. It serves more like a traditional formwork, probably staying in place formwork. So I think it's just this kind of trade-off between structural reinforcements and the geometric flexibilities that we're still looking at, if we can still maintain that like structural reinforcement even if we deviate from the circular tube. But at the end of the day, it still have the benefit compared to the traditional formwork being very lightweight, being customizable. So regarding the collaboration, I think it's an interesting element in the way in Australia where PhD is organized. So for example, each PhD, normally they have a supervision panel. So for example, if I'm the main supervisor, I contribute to about 50% or sometimes 60% of the supervisions. But the PhDs, normally they would have 1 or 2 actual PhD supervisors. So for example, the student who are working on the FRP project, he has 1 supervisor from the material team who are expert in FRP, and another supervisor from the structure, like the civil engineering. So 1 from mechanical engineering and 1 from civil engineering. And he would consult all of us, and he would have exercise to the FRP lab and the structure lab. So I think this is a very efficient way of creating collaborations. So the students are motivated to integrate multidisciplinary knowledges, and he would sit into the monthly exchange research sessions in different curricula, different schools. Yeah.
Great. That's a very remarkable setup. Yeah.
Thank you.
Thank you.
If there are no other questions, maybe we should move to our last presenter and we can still continue discussion afterwards, of course. So our last presenter of today's panel is Hua Chai, who is a researcher at Tongji University. So please take it over.
Introduction. Can you see my screen?
Yes, but your microphone's a little quiet. So if you could try to speak a little closer to the microphone would be good.
Okay. Is it better now?
Yes.
Okay. Good morning, everyone. And this is Chai Hua from Tongji University. And I'm now a postdoc researcher here. And today my topic would be platform-based robotic wood architecture. Since 2014, we have been involved in the research of robotic fabrication of complex timber structures in Tongji University. and a series of workshops, exhibition, and practice projects had been carried out in collaboration with Fabrication, Aki-Uni, and ICD Stuttgart. Working with timber is of great significance in the context of an increasing emphasis on the carbon neutrality. Wood is a natural and renewable building material that could store carbon, and it had been regarded as one of the most promising building materials for the future. When we look into the timber construction industry today, different kind of specialized timber machining center is developed to automate the prefabrication process of some existing timber structure system, like the lightweight frame structure. And in the process of this automation, the flexibility of the production system, that the flexibility to be adapted to different systems have been getting lower and lower. In contrast, the academia field has witnessed the emergence of a lot of innovative timber construction system in the last decades, which takes the robot as a new generation of tools. The robot, as we all know, could be integrated into the design phase through the parametric control and show higher adaptability to different systems. So a new trend is the development of this kind of robot platform that could integrate the cutting edge achievements in the research field and try to immigrate the new research into the industry. And we can see the construction process is already being redefined by this kind of robot platforms. Common types of platforms are the fixed platform, like the gantry robot system, and also the transportable and the mobile robots, and even the swarm robot system. For timber construction, there are two types of construction paradigms or scenarios: the offsite prefabrication and the on-site construction. So in our research, we try to rethink the construction, rethink the potential of this two construction scenario based on the possibility that is brought by the robotic construction platform. So for the two types of construction scenario, two types of robot platform have been developed in our team in Tongji University. One is the prefabrication platform, and another is the on-site fabrication platform. And the prefabrication platform takes a fixed gantry system, and it is developed targeting at the customization, mass customization of a complex timber components. And the on-site mobile robot platform could really move on-site and assemble and conduct automatic assemble tasks on-site. And when we talk about the platform-based robotic fabrication, we are not only talking about a question of automation or just equipment development, but also talking about the opportunity for the innovation in architectural design. So in this context, our team is interested in exploring the interaction between the robot platform and the building system by developing some new solutions to different challenges in the industry. And so today I will show two application example. So for the robotic prefabrication platform, I will take the double curved glue line production, one of the very challenging problem in the field, in the industry, at the application scenario. And for the on-site mobile robot platform, we will mainly focus on the in-situ construction of a new type of spatial glue line. So first, I will introduce the robotic prefabrication platform. And this platform is initially developed by Tongji University together with Fabrication since 2015. And a 6-axis gantry system is equipped with 2 KUKA robots that could provide a sufficient large-scale fabrication capacity for robotic fabrication experiments and practice. And also a set of robotic timber fabrication and processing tools is equipped as a tool library, and including a gripper with automated nail gun, a universal milling spindle, a chainsaw model, and also a bandsaw module. So also a set of infrared camera system are equipped to give the system the ability to see the environment and also the robots and the materials. So the information collected by the camera could be directly transmitted to the design platform Grasshopper in real time, which is used for the high positioning of the robot and the materials. So with such a robot platform, we want to take advantage of it to deal with the challenges of mass customization of complex timber components. So this project, the nomadic wood, is an installation developed for UABB 2019 in Shenzhen, and which aims to tackling the customization of double curved glue line structures. And as we all know, there are 4 types of curvature in glue line in practice. And the first is straight, and then single curved ones, double curved with no torsion, and then double curved with torsion. So this installation is designed to be a non-freeform glue line beams that intertwine with each other. So all the beams is double curved with torsion, and while the straight and the single curved beams could be produced with current technology in the factory, and there's still no efficient way to produce the double curved ones. But robotic bandsaw cutting technique which could cut the root surface with high efficiency and accuracy have been proved to be one feasible solution for this double curved glue line production. And it works in a similar way to maybe the hot wire cutting process, but it's more complicated because the bandsaw blade have twice. It had to be parallel to the cutting surface all the time during all the process. And also the bandsaw cutting process takes the straight or single curved glue line with uniform sections as input. And so it can be well merged with the current production process for glue line. And the bandsaw have a lower curve width and lower noise level compared with some other timber processing tools like the circular saw, but it also have its own limitation, like the accuracy is difficult to control, and which is determined by the flexibility of the saw blades. So that also means we have some constraints brought by this new kind of tools. So that's why we try to investigate the cutting capacity of bandsaw in root surface, which can be an important parameter that affect the final design. So the premise of bandsaw cutting is that the saw blades could achieve the required rotation in the curve within the width of the curve. So we make the cutting experiment on the ability of the saw blades moving along different arcs with different radius, and also we tested the ability of the bandsaw rotating and tilting along the different root surface to model the different factors that could influence the ability of this bandsaw cutting process. And the capacity of the result of the test could be used as a constraint in the computational design process, and to analyze and optimize the curvature in the installation design. And also the cutting capacity of bandsaw could be reflected in the construction system and tectonics design of the final system. A large-scale continuously double curved beams is divided into 8 small segments according to so in our case, we use the curvature-based subdivision method that was developed to improve the material efficiency while also ensuring the design comply with the tool constraints. Each beam is divided into 8 segments with different lengths, and there are 72 double curved segments in total. Each of the double curved segment is expected to be cut out of a single curved glue line with a minimum volume that cover this target segment. So we can, in this way, we can reduce the material waste and also improve the grain continuity. And to reconnect the small short members into a continuous glue line, we normally additional connectors, steel connectors, like a screw of steel plates would play an important role. However, the large number of joints that with different angles and size would pose a great challenge for the production of both the timber components and also the steel connectors. So in this context, we are inspired by the traditional interlocking joint and design this kind of scarf joint, which is a traditional approach to join two wood elements end to end, which is widely used in traditional construction to produce long members with short ones. And the joint is modified to be produced with a robotic milling process, and it could be a very fast assembled on site with just hammering the additional blocks. So, since each segment is a double curved members. The mass customization of the all the segments is actually the major challenge in this project. So we make full use of this dual robot system, and the two robots are responsible for milling and bandsaw cutting respectively. And with one robot equipped with a spindle and another equipped with a bandsaw effector. And in this, we use this modified 14-inch bandsaw that is mounted on the robot to conduct the root surface cutting, and with orderly organized of the saw cutting and the spindle milling process, the robot could perform all the fabrication tasks in a continuous workflow. So this is a final installation in the exhibition in Shenzhen, and I think this project is also designed to demonstrate the ability of the robot platform in this kind of mass customization of complex structures, and it could well we also hope that the freeform structure could be a display of the potential of the robot platform's morphospace. So this is the first project, and the second part of my presentation will be will mainly address the on-site mobile timber fabrication platform and the spatial glue lamp system we are developing. So this research starts with the concept that despite the main advantage, the current prefabrication timber structures is still suffering from the constraint of modularization or standardization. And for timber construction, actually, there's still no on-site construction system that could be comparable or competitive with on-site on-site constructions of reinforced concrete structures. So in this work, we are aiming to tackle exactly this problem of on-site timber construction system with by developing this customized mobile robot platform. The platform is developed to be flexibly moved and deployable for various on-site timber construction tasks. And the platform consists of an industrial robot mounted on a track platform, and also with a customized tool processing station equipped to conduct timber fabrication tasks. And also real-sense camera is mounted on the robot to localize the robots on site. And the reach envelope of this robot is developed to cover both the typical height of a ceiling and the floor work area. And a gripper with automated nail gun is mounted on the top of the robot to grip the components from the storage and then apply glue and the base beam and finally nail the beam. And the timber structure could be robotically assembled on site with by repeating this kind of continuously fabrication routines. So we assume that this kind of construction system with robot on-site nailed and glued components could be regarded as a new kind of glue lamp structure, which is an extension of the traditional or a common concept of the glue laminated timber. So based on this possibility, we try to explore the new new design potentials for timber construction. So we first conceptualized the system called the glue line beam networks, and it is assembled by the robot from beneath a slide to reinforce the structures for potentially multi-story buildings. And at the heart of this building system development is a material efficient beam networks that is comparable with the capacity of the robot platform. So in our case, we the system is designed to be composed of discrete timber sticks that is iteratively placed and joined and connected with nails and glue. And the computational design of the system could directly take the result of the structure optimization process. And we did a basic combination of the sticks, of the timber sticks is composed to generate the timber beams, the continuous beams from the beam axis. And the sticks arrangement also allows could adapt to different situation in the axis within like the converging and branching streams within this multi-directional support networks. And then with this basic combination, we developed this. The difficult to design this beam network is the negotiation process between the fabrication constraints and also the material property. So in this case, we developed this agent-based modeling process that could adaptively arrange the sticks according to the different constraints. So all the agents could iteratively interact with each other to meet all the fabrication constraints and also avoid the collisions as much as possible. So with this system design, we make this case study prevailing last year as a demonstrator of the proposed system. And it's also a collaboration with Fabrication and ICT Stuttgart. And the pavilion consists of 2 CLT roof panels supported by 8 columns. And the above mentioned beam networks is designed under both roofs to enhance the load-bearing capacity of the CLT panels. And the construction sequence can be summarized as first we will erect the columns and the CLT panels, and then the robot will be moved on site to iteratively assemble the timber sticks underneath the structure to reinforce the slab so that the load-bearing capacity could be enhanced, and the 2 roofs will be fabricated by the robot one by one. So first, we will hoist the roof panels in place, and then at the construction site, the robot could locate itself by identifying the markers that is pre-embedded on the roof panel. And we use the total station to collaborate all the markers. And during the fabrication, once the robot is moved, it will collaborate the nearby markers with the Intel RealSense camera to locate the route of the robot in the environment. So after the mobile robot is localized in the environment, the robot could grab the elements from the storage, apply glues at the glue station, and then place the element in place and fix it with multi-nails. And the mobile could, the mobile robot could assemble the timber sticks into this continuously integrated structure with gluing and the nailing process. And this is the final result. The glue line beam networks actually reinforce the roof. The roof could achieve the maximum span of 5 meters with a thickness of only 60 millimeters. So the analysis of the final result also show that the pavilion was constructed with very high precision, and with the error distribution mainly concentrated within plus or minus 3 millimeters. This also proves that the robot could perform high precision construction on site, even taking into all consideration of the construction errors and also the robot repositioning errors. So also we should admit that the technology is still in its infancy, but some of its features also could make it very promising for the future, even in the multi-story construction, like the very important factor that it could adapt to the network floor plan instead of the grid floor plan in the current multi-story practice. And so this, we assume that this research could be a valuable start point or reference for the more flexible and more flexible multi-story design construction. So another system is the glue-line beam network is the first system we developed with the mobile platform. So we want, on the basis of this system, we want to go one step further to extend the planar beam network into a spatial glue-line beam networks. So we take the traditional lightweight frame structure as a prototype, which usually assemble prefabricated standard columns and beams into the orthogonal spatial grid. So we make a preliminary attempt last year in the Digital Future workshops to test the system. And the pavilion is designed as a structure around the steel column, but the structure is self-supported. So first, the structure tried to extend the flexibility of the frame structure. So we introduced the 45-degree oblique members into the traditional orthogonal frames. So the different combination of these oblique members with orthogonal grids will greatly increase the complexity and the diversity of the final result. So we first make a topological study on the different combination from single axis to planar orthogonal, spatial orthogonal, and the planar oblique, spatial oblique. And we also define the assemble sequence of the different joints in this process. So the robot assemble logic could be well embedded even in the design process in the very early stage. So we also take the topology optimization as a tool to find the layout of the frame axis, which is actually a series of polyline composed of only horizontal, vertical, and 45-degree. So for a given frame axis, we can a special glue-lamp structure could be generated by first analyzing the joint types and then select the corresponding joint in this library. And the robots would localize itself and fabricate in a very similar way with the previous project. This is a small video of the on-site construction process. The robot program could instruct the robot to grab the sticks, apply glues, and place the stick. And a human operator will hold the nail gun to fix the sticks in place. And the structure is actually composed of more than 900 members, and the on-site construction process of all the sticks takes around 10 days. So, so last I want to show design exploration in our workshop last year, and while we developed the pavilion, we also launched an online design workshop that explore the possibility of this kind of spatial glue-lamp structures, so which gains a lot of wonderful design exploration. So this is one of them made by Fabian and Desmond, which is a redesign of traditional lightweight wood frames construction with the new logic of this kind of mobile robot construction. So here we can see the potential in extending the robot on-site timber construction into the existing construction system and into the industry. Okay, that's all my presentation today. Thank you for listening. Shall I?
Yeah, you can stop sharing screen. Thank you so much. So you're the last presenter today, and I think that we can have a lot of questions for you and for all of the speakers today about generally the topic, fabrication, and how assemblies are working. One of my questions for you is working with wood, because it's a natural material. It has a lot more anomalies and variation sometimes in the wood. And do you ever look at the types of wood or how the wood itself is working structurally when you start to look at the designs? Or is it all more, maybe other people on your team are working on that direction while you're focusing on the fabrication direction? But I think that that's a very interesting thing.
Actually, when we start our research on the robotic fabrication of timber, we get our experience in one practice that we collaborate with one of our industrial partner, and that's where we learn what material is normally used in the practice, and what's the challenge of the maybe both the design and the application process. And like you can see, the first pencil cutting project is actually based on one project that we are involved in, which is a project developed by Aki Uni, and it's a very large vault structure with a large scale curved glue-line beams. And when we get involved, we also realize that the limitation in the material properties and also the production process is that they can only, we always want the fiber, the grain of the timber, of the wood could be, could follow the workflow as much as possible. But when they try to produce the beams in the design and even in the factory, there's always a problem that they can only make it a single curved structure. So that's why we take that project as a starting point to explore how we can make this kind of double curved or even more complex glue beams. At your side, we also trying, after we developed the system, we are also trying to make a different practice or experiment to see how it could be fit back to the industrial. So I think it's just the collaboration with the industry and also the collaboration with our design teams or design company like Akiuni is that's driven us to get better understanding of the material and to like tackle the different challenges posed by the different process.
Thank you. That actually answered my question perfectly, even though my question perhaps was not formulated very clearly. I wonder also if there are any questions from the audience, attendees. You can raise your hand or put questions in the chat, as well as viewers on Bilibili and YouTube could raise some questions as well. But I would also like Philip and obviously Nick Bao, who are here, and Dan Lo is here for a few more minutes. If you had questions or comments on each other's work, it would be great to discuss that at this time.
Sorry, maybe, sorry. Yeah. Maybe I'll just pop in one last question before I have to pop up in a few minutes. So because for Dr. Chai, because in Queensland, we also have a big timber research lab called Future Timber Hub, which are partnered a lot with local industries. But during our conversation, we did notice there is a conflict between mass customization and the ability to scale up for industries, because for most of the timber production, at least in Australia, they're working with huge volume of productions and construction projects. So sometimes they are more interested in how the automations can be applied in the existing flows and can be quickly scaled up across the industry practice to either make an impact or like recoup their, let's say, investments. So I'm just wondering, what's your stance on this, and how would you see maybe our or part of the system that you have developed now could be quickly scaled up across, let's say, timber industry, timber constructions, and etc., instead of applying maybe let's say a few, of course, very well delivered, inspiring projects. Thank you.
Thank you for the question. And actually, I know it is true that the common paradigm in the real industry of timber construction, they emphasize on the automated fabrication and the design of maybe modular construction or standardized production that could be very fast produced. And that's also how the market is operates. That's where they can gain the most of their benefits economically. But we can also notice that the problem, like I have showed in the multi-story buildings, the fast fabrication and the modularization will result a very standardized design. And for me, when I'm thinking about the mass customization of this complex timber structure, I'm thinking about maybe when we want to make this this kind of large volume timber constructions, we can gain more freedom in the design system. So today, what I'm showing is a very specific problem, and as I explained before, the double curved glulam maybe now is one of the application scenarios in some very important large-scale timber project, like some very important timber projects, like the Pompidou exhibition hall that is designed in Nice. Also some projects in Europe. And so my research of the glulam structure aiming at some of the specific type of project. But when we talk about the mass customization, I think it's also a great opportunity for the industry to maybe when they can use the robots and make the fabrication process more flexible and adaptable, and it could be adapted to different kind of changes in the fabrication system. Maybe the result of the timber construction, like the multi-story buildings and even the fast fabricated lightweight frame structure, could be more customized design by the users. And I think the opportunity lies in freedom that provided by the robots. Even though now maybe also in my research is not so obvious in the industrial scale, but I think it's also one very promising for the future for the industrial. I don't. Is that could that question?
Yes. Thank you very much, Dr. Chai. Yeah.
Thank you for the question.
I think I have a question to all of you. It's a great presentations, I think, from all of you, showing the scenarios of the PhD and young scholars. Actually, you especially integrate different knowledge from multidiscipline collaboration, which is extremely interesting, important, actually can contribute to the other discipline. And the most challenge actually to all the researchers is not just about the imagination and creativity, to define a certain kind of working flow and the procedure, and then to prove it by the pavilion. I think this is the first step to set up the research, and that is probably a certain kind of paradigm, and the evidence-based working flow is a research methodology to change, the industry and mass production industry. They're including the timber structure, actually in the whole world, I think it's already very developed. And the scale of the components, the efficiency, and the procedure for the construction have a lot of standards. It's really difficult to redefine another system and talk and teach them this is better than that, and probably the working flow, how to educate the workers, and how to define the standability or the regulations and policies from the government to agree to construct a building like this. So from experimental mock-up research, prevalent research to the industry, we need not only the knowledge from the architecture perspective, but also we need to prove it. We need to prove the result and especially the procedure, and that is extremely the challenge. It's not just install a building, put it there, but it should be stable enough, safe enough, proved by the different tests, including the shaking test, earthquake test, and the compression test, tension test, sharing forces test. It's a lot of knowledge we need to achieve and learn from actually the civil engineer or the other disciplines. So we find it's a great challenge. That's why I put forward the question to Luodan, how they educate the PhD candidates. I think Chaihua is actually have the background to have based on the collaboration between Tongji and ICD Archimag's team. We have around 7 workshops already collaborate over the past few years. I think we're learning a lot from them, but still we notice that's not enough. Maybe the next step, firstly, is not just, I think it's like prevalent research. Actually, that's why in our team, we have very strong design teams and fabrication teams. We need to prove them by the whole procedure in the architecture discipline as a robotic fabrication research. That's not just the artwork, rather than the artwork, the architecture mansion, architecture building actually have a totally different definition. This is systematic ways to make further deep research on the details, on the system, and also on the procedures. That's why I think that is that probably a future for the such kind of robotic fabrication or competition design that should be reset up and reorganized or to another department. Maybe that is so deep for so many new scopes, and the new horizons actually is totally different system paradigm of what we already get to educate. So it's more like collaborative overlap to each other from different discipline. For example, you need to understand robotics, you need to understand civil engineer structure knowledge, and also you need to have some creativity to design have the design thinking to organize, establish a system to not only to the result of the building, but also to the process, how to design the special tools, and also how to scripting software to control the robotics. So that's a totally new scopes in the architecture discipline. I think probably it should be furthermore discussion and furthermore researchers, PhD students who should engage into this research topic. And I have a special question. That's the general comments. I think the research is not deep enough for all of you. It's just like a formalism. It's like a manifesto, or you put forward a possibility. It's not the real architectural skill things, and it's a long way still going to even further for all these kinds of researches. So I have a special question to Nick on your research and on your research based on the collaboration from Roland Stoke and your studio. I think you're doing some like 3D carbon fiber and glass fiber printing, and define the materiality, inner inner structure and out structure. That's like you have different loops of to integrate them together. I think that's extremely important to have a multi-material printing printing system for the future 3D printing technology. So the challenge will be extremely difficult because two materials need two extruders, right? And we need to establish a very complicated printing process. And sometimes because of the geometry is extremely complicated, some diagonal or zigzag geometry need to define the process of the printing toolpaths and effectors, because some material is too close to each other. You want to make a sharp turn, and that would be very very difficult crash between these two materials. So I'm very curious on that details and wonder how you achieve such complicated form based on this two material collaboration. Could you introduce a little details on this kind of black carbon fiber printing and the glass fiber 3D plastic printing outside, how you achieve such kind of result? I'm really curious on such kind of details.
So this project is actually is led by another PhD student by Roland Stokes, which Hassan Mohammed. So he also introduced the design and the fabrication process in 2020 Digital Future conference. So the main idea is to design the envelope and print the password. Then we design the small conduits into the envelope of the geometry. So we leave the one space for conduits. Then we put the carbon fiber stream into the conduit, then cast the resin to make it solid. So we leave the space internally.
It's like you cast the material, it's filling another material into this printing volume. It's not two material. Okay, I understand. Mm-hmm.
Yeah, it's not two material printing. It's we just print the formwork, then cast the resin and the carbon fibers.
Okay. Mm-hmm.
But it's a good suggestion. Later, we need to develop the multi-material printing better than just one material printing.
Okay, understand. Good.
I'm quite interested in the Dr. Chai's the progress, and we also discussed before using the topology optimization and swarm intelligence for your timber construction. So later we might can discuss further about the integrate with the multi-region and the topology optimization for the fabrication. I think will be more interesting.
Yeah, that would be great. We can.
Yeah. So I think it's also an interesting direction to integrate swarm intelligence, generative design with the structure performance simulation or optimization. I think maybe your PhD thesis is on that direction, right, Nick?
Yes. Yeah.
Mm-hmm. Mm-hmm.
But we haven't.
One of the scenario, right? Timber structure is one of the scenario for that. Mm-hmm.
Yeah, and we haven't developed into the real systems. So maybe later we can develop a Grasshopper plugin, or now it's all based in the Python algorithm using the original modify BSO method. So it's not all other designer can use, but later we can improve it.
Mm-hmm. Good. So I'm interested in your PhD thesis. So when would you like to publish the paper?
This year.
Yeah. Okay. Okay. Looking forward to read it.
It also looks quite interesting, and I think I've seen one of your presentation, and the algorithm really great that you can use the agents to interact the agent according to the structure simulation and optimization process. And also I'm also interested in this kind of design, and also I'm more interested in the materialization process. It will also be a great opportunity if we have the opportunity to maybe extend your methodology into the material system, like a timber or different building system. And I think we could talk about this in detail.
Thank you.
Virginia, I think you can make a conclusion.
Yeah, I think all the presentations were really wonderful. Dan had to leave, but for sure, I think it was really interesting to see the different materials working with fiber reinforced materials, and then Nick's work, which includes fiber materials, but also a wide range of materials from casting concrete to 3D printing plastics, and then looking at wood as another material, and how robotics and fabrication help us build with all these different materials. My own research is material based as well, looking at knitting. So I think it's really interesting to see the different approaches, but also the overlaps and similarities between these materials. One thing I think is really important is the process of making and working with the machines and the tooling. I think all of the projects we see this kind of analysis into tool paths and into how the machines have constraints, the different ways that the robots can move, or the thickness of the bandsaws, turning radius. So the way that we work with machines and materials is really important in this next phase of design, building, fabrication. So I think this research is really cutting edge for many of the students to be looking out for. And so I hope that I can see the developments of all of your work in the future and of the students that are here watching today. Hopefully they've learned a lot and are going to be the next generation building on this as well. So thank you so much. And thank you, Philip, for your questions and comments as well. And thank you to Dan Lowe, Nick Bao, and Hua Chai for your presentations. And please do not forget, everyone, that we have another session tonight for the Young Scholars Symposium on AI, Human and Machine Interaction. So please tune in again. Thank you. And have a good day.
Thank you.
Bye-bye.